Last time we talked about the outline of our course and give you some introduction phase transitions in general. So today I will give you some concrete examples in classical systems, and I will define what I meant by scaling and critical temperature and universality class. There will be 3 examples classical phase transitions this lecture hour. So the first example is a liquid-gas transition, as shown in this plot here. As a function of temperature and the density of the fluid, the sum liquid shows the phase transitions between the liquid and the gas phase. And there is phase boundary between these 2 phases. But the interesting point of this liquid-gas transition is that there is coexisting phase where we can see this mixture of liquid and gas under this yellow curve as a 2-phase region. There is a critical temperature Tc here, below which we can have coexisting regions of these 2 phases. But above this critical temperature, there's no distinction between this gas and liquid phase as you continuously change the density of your fluid. So from one side to another, the gas or liquid become another phase in a continuous fashion. So this is called a 1-phase region. So between 1-phase and 2-phase region, curve called the coexisting curve, and if we fix a temperature below Tc, we change the density of fluid, and we can see that it is not possible to actually reach the other side of the phase without passing through this coexisting phase or the 2-phase region. So for example, from gas phase, and if you fix a temperature like here and increase your density, and you'll find that at some point you'll cross this yellow curve and the system will become the coexisting, where this liquid and gas mix up. And then you pass another branch of this coexisting curve and finally reach the liquid. However, if I'm here, I can continuously change the gas of the system and without passing through this 2-phase region, and finally the gas becomes liquid. So it's a continuous evolution of the system. So this is a very interesting point, the Tc, which separates this 1-phase and 2-phase region. On the other hand, if I start from this temperature below Tc, like here, I can avoid passing through this 2-phase region by following some kind of a detour path where you first keep the density fixed, but you increase the temperature up here, and then you change the density by fixing the temperature like this. And then you lower the temperature again to the temperature that you started initially, and finally, you complete this evolution from the liquid phase to the gas phase without passing through the 2-phase region. So that's the detour that you can have to get a continuous evolution of the system. And the interesting question to ask are the shape of this coexisting curve. So this is defined by the difference in this density of fluid, say nearby this critical temperature Tc, which I define this as rho plus and also rho minus. So the difference between rho plus and rho minus is a function of T minus Tc or Tc minus T, and to the power beta. So that is the shape of this coexisting curve, and which can be determined experimentally. And this power law behavior is a signature of a phase transition, as I mentioned. This beta could be found experimentally, which is 0.327. That's for this material, SF6. And this is approximately the same value for a different system. It's a liquid helium-3. So you can see this beta critical exponent is irrational number, all right? As I mentioned last time, that this can be a rational or irrational, but in many cases, these exponents are irrational value. And as is shown here, experimentally, it is found that this is 0.3 or 0.32, and the same critical exponent is found in another liquid gas transition, which is the liquid helium-3, and this exponent is found to be exactly 0.32. So in other words, there's some general aspect of this liquid gas transition of this type, and this exponent beta is irrational value, and also it applies to many different liquid gas transitions of this type for different systems. They all behave with the same in the sense that the beta is the same. However, we will see later that this beta could be also estimated from the dimensional analysis, as we mentioned last time. So by power counting the scaling dimension of these variables, and you could derive this exponent beta, and we'll see later that this beta coming from this dimensional analysis turn out to be 1/2, which is a rational number. So you can see that this is, of course, it is wrong, and this must be correct, okay, because this is experiments. You may wonder why there's a difference between this dimension analysis and the actual critical exponent observed in experiments. Okay, so this will be one of the topics to discuss later. So the lesson that we learned here is that dimension analysis is not very reliable in many cases where we can find this transition. A second example, which is the magnetic critical points. So as I briefly sketched last time, there are some magnetic materials which shows parallel orientations of the all spins, or the all spins are aligned along the same direction. The typical example is the ferromagnet. So the ferromagnet is kind of a material where there's some spins left over from the outer shell electron configurations, and so the electronic spins could actually interact with one another. They form this parallel orientations of these spins. So let me just formally define this ferromagnet. It's a set of atomic dipole or spin crystal lattice, and the spins interact with each other on a short distance scale. Say, for example, the spins interact ferromagnetically with the neighboring spins. You could imagine that all the spins on the neighboring sides are coupled by those kind of so-called spin exchange couplings, which we call this J ferro. And that is the origin of this ordering in the ferromagnet. At large temperature and zero field, the spins are in this paramagnetic phase, and there's no net magnetization, meaning if I calculate the magnetization on each side and take the average, and this is 0 in the high temperature limit. So maybe I can remind you of the phase diagram of a ferromagnet. This is the magnetization, and this is temperature, and you can see that this is a TC curve, and below TC curve you get perfect alignment of the spins, and above the TC curve the spins are randomly distributed. Okay, so there's no net magnetization, but below this TC curve there's some finite net magnetization. So that's the ferromagnet. You could probe this phase transition by increase the temperature like this, so that the magnetization will decrease as a function of increasing temperature at higher temperature. So you lose all the magnetization and the system becomes a paramagnet. However, for T less than Tc, you get magnetization. Macroscopically, we could describe such a transition from the ferromagnetic phase to the paramagnetic phase. Okay? And especially this Tc curve will go down from finite value to almost 0 right here. So this is when Tc, so magnetization vanishes right here at Tc. So we can actually probe this experimentally by increasing the temperature of the system, and the magnetization starts to decrease, and then finally when temperature reaches Tc, and you reach the paramagnetic state. Okay, so and this transition is actually continuous, and we are interested in this region where this magnetization almost vanishes near Tc, and we want to see how this magnetization behaves as a function of T minus Tc. So let me just summarize power law behavior of the magnetization of a ferromagnet. Okay, so for example, the Ising ferromagnet, and you could have this magnetization M goes like Tc minus T to the power of beta, and this beta is around 0.313 plus minus some error bar. You can see very clearly that this value beta agreed almost exactly with this liquid gas transition. So this is the same as in the liquid gas transition. So rho plus minus rho minus proportional to Tc minus T power of 0.32. Almost perfect agreement regarding the critical exponents between completely different systems, say the Ising ferromagnet or antiferromagnet and the liquid gas transition. For example, this liquid helium-3. This is another coincidence that you can find by chance. There's a deep connection between these two systems regarding the critical behavior. Deep link between these two systems near the transition. And this link, as we will see later, is called universality class. Okay, so in other words, this Ising magnet is belonging to the same universality class as the liquid gas transition. Okay, so even though these two systems appearing to be very, very different systems, but near the transition, they behave almost the same. Before I introduce to you the third example, so let's summarize these two transitions. One is the liquid gas transition, another is the magnetic transition. For a magnetic system, so it is very interesting to know that the thermodynamics of a ferromagnet and antiferromagnet bipartite lattice are identical. First, define this antiferromagnet as the orientations of the spins such that on the neighboring side the spins are antiparallel, like this. And so this is in contrast to the all parallel spin orientation of the ferromagnet. And we will define this model Ising later. So that simply just tells us that the spins can only point to the z direction. But in general, the spins can actually lie in any directions in three-dimensional space. But for the Ising system, the spins align only along the z-axis. So there are some classes of materials which shows the antiferromagnetic long-range order. And on the bipartite lattice, so let me just define the bipartite lattice. This simply just tells you that, for example, on the square lattice, you could divide this lattice in two sublattices, say sublattice A and sublattice B, and A sublattice and B sublattice are identical except that they simply just shift by a lattice constant. And such lattice are called bipartite lattice, okay? Meaning you could simply just divide your lattice into two groups. So that's the meaning of this word bi. But on the triangle lattice, for example, it is not bipartite lattice because you cannot separate this triangle lattice into two subgroups, A and B, but you could do that on the square lattice. On the bipartite lattice, both Ising ferromagnet and antiferromagnet, they obey the same critical behavior, namely the magnetization goes like Tc minus T to the power of beta, and beta is about 0.32. And this is the same as this liquid gas transition. And the exponents are excellent agreement. Well, that's just observed by the experiments. We'll see later the connection between these two, which is the universality class. And we will analyze and study in what sense can we call these transitions identical and they belong to the same universality class. So now let's look at the third example, which is the superfluid transition or lambda transition in liquid helium-4. So this is also a very well-known example in solid-state physics with the old tradition. So this is a phase diagram of a liquid helium. It has this famous lambda transition, and phase 1, normal fluid, and this is phase 2, a superfluid. So we will describe the phenomena of the superfluid later, but in short, a superfluid is a fluid that's without this viscosity. Consider this as a perfect flow of the fluid without the kind of dissipation or this viscosity and so on. And in terms of this charged particles, the superfluid is kind of superconductor in the context of charged particles. So in the superconductors, electrons can move without kind of resistance. Okay, it's a perfect conductor. So you can consider this superfluid as a perfect fluid without friction, without dissipation. And liquid helium-4, general phase diagram, but it also has this solid phase and a gas phase. So of course, in low temperature and high pressure region, this is a solid, and in this low pressure, the high temperature region, this is a gas. But in between, there's a normal fluid and a superfluid region. The so-called lambda transition is a transition between a normal fluid to the superfluid of a liquid helium-4. So the word lambda in this lambda transition refers to this shape of the specific heat near this transition temperature. This is the shape of the specific heat, and this is T lambda. You can consider this is your T lambda here. So at the critical temperature or lambda transition temperature, specific heat of the liquid helium-4 seemingly divergent. Okay, like this. So later we'll see that this is not a true divergence. So, and the shape of this divergence looks like a lambda, and that's why we call this lambda transition. So historically, divergence was fitted into the logarithmic function near this T lambda. So C is approximately given by, say, log T minus T lambda plus B for T greater than T lambda, and A prime log T lambda minus T plus B prime T less than T lambda. This seemingly logarithmic divergence in specific heat goes like a log. However, as we know, experimentalists check very carefully with a high accuracy measurement near this lambda transition and find out that this is not a log. Okay, this is really a cusp. So the cusp is a kink-like geometry with a very sharp edge here, but it's finite. So right at this tip of the cusp, this specific heat doesn't diverge. Okay, it is not infinity. However, a logarithmic divergence indicates that this values of the specific heat goes like infinity. In reality, or a more careful measurement indicates that this lambda transition shows a cusp rather than a logarithmic divergence. So the behavior of the cusp is a power law. So C proportional T lambda minus T, power of 0.013 plus minus 0.03. So that's the more accurate results. So this kind of a singularity is really tricky because you could very well fit this seemingly divergent curve by two different functions. One is a log, another is power law. So which one fits better? You don't know until you have a very high accuracy, high resolution experiments. We are confused by these two different fittings. The reason is that very close to this cusp or this divergence, we can actually convert power law to the log and the log to power law in a Taylor expansion. Right? So it is hard to distinguish this power law from exponential or log. And the reason is that C is proportional to, suppose there's a little t, which is a dimensionless parameter relative to this critical temperature that we defined earlier, T minus T lambda divided by T lambda. If this specific heat is proportional to T to the power of alpha, and I could tail expand. I could re-exponential e to the alpha log T, and I could tail expand this when this alpha log T is not that large, and up to the second order. And if I keep only up to the linear order in log T, I get the log T. So this power law, after the constant shift, becomes a log function of T. But this kind of expansion holds on the condition the x power of n is actually e to the n log x, and it's approximately given by 1 plus n log x. And this is accurate only when n is much less than 1 and x is not too small. But this condition can be easily satisfied close to the lambda transition. And that's why people did not realize that this is not logarithmic divergent. Instead, this is a cusp, but only when we have a very, very high accuracy measurement, as high as pi, which is about order of 10 to the minus 8, that accuracy in determining this little parameter t in experiments. So if we have such a high resolution experiments which can tell up to small amount of deviation from this T lambda, and only then we could tell this logarithmic from this power law. So far, I have given you some examples of this phase transitions at finite temperatures, and there are some general features of this phase transitions, namely observables shows power law behaviors as a distance to the critical temperature, and there are some relations of these critical exponents among very different systems. And it seems that they belong to some universality class, but we don't know what that is at this point. So next time, we will talk about a very general level from the statistical mechanics on the partition function, and we will ask these important questions regarding to this phase transitions at finite temperature. For example, we will ask this very basic question: why do this phase transition occur at all? Because from this partition function, do we expect singularity or some kind of singular behaviors when we calculate this partition function? So we don't really know why that should occur. It should because it is what we have found experimentally. It exists in nature. It should follow the principle of a statistical mechanics. But where? Okay, so we're going to study where is the trick that is hidden in this partition function. And we will also ask the question, how do we calculate this phase diagrams of the system changes as a function of the tuning parameters, such as pressure or temperature? How do we calculate this phase diagrams? Further, we will ask the question, how do we calculate this exponent that was observed experimentally? And then finally, the most difficult questions that we want to ask is, why does this universality class occur? Well, why do we expect this exponents of the very different systems to be exactly the same? And why does it occur? Okay, what is the principle behind this universality class? Okay, so this kind of a general questions are the questions that we want to address in the following lectures. Please stay tuned, and you will be amazed by this beautiful experiments and beautiful theories. Okay, so I'll see you next time.